So thanks everyone, and we are very happy to invite Dr. Piotr Kawa to give our today's work. And he is a researcher at Roosevelt University of Science and Technology, and also currently working at Resemble AI. He works on audio deepfake detection with an emphasis on building generalizable and robust solutions, and also working on multimodal fake detections. And welcome everyone to join, and really happy and really appreciate that you accepted our invitation. Thanks for your time, and it's on your.
Thank you very much for having me. Just two quick checks. Can you hear me and do you see my presentation? That's
Yes.
great. Okay, so hi, I'm Piotr. As Lynn has already introduced me, I do research at Wrocław University of Science and Technology and also at Resemble AI. Today, I would like to talk a bit about generalization and robustness of audio deepfake detection. In my opinion, there are two main challenges that we currently face in our field, and I would like to share with you a little bit what we did in these two topics. So first of all, let's start with the task that we're facing, audio deepfake detection. So we would like to determine whether the sample, the audio file that we're currently analyzing, was it spoken by a human being or rather generated using AI tools. Currently, so the samples are generated using AI, but we also evaluate them using AI tools. For that, we typically use deep neural networks. We can analyze either raw audio or use some intermediate step for feature extractions. The final decision, the final answer that we're returning is we determine whether it's spoof, so fake, or bona fide, that is real. My PhD thesis was titled on generalization and robustness of audio deepfake detection, and it covered few papers. Today, I'd like to talk a bit about two of them, namely attack agnostic data set towards generalization and stabilization of audio deepfake detection, and defense against adversarial attacks on audio deepfake detection. I'll also mention a bit about our recent work, and that is MLAT, multi-language audio anti-spoofing dataset, and deepen penetration testing for audio deepfake detection. So let's start with generalization. What is that? We often notice that there's a degradation, unfortunately, oftentimes significant, when we analyze samples that are different from what we saw in our training data sets. And what does it mean that it's different? So the samples that we see on the internet, these so-called in the wild samples, differ in terms of the generators that were used to generate these samples. Quality, they're often distorted. There are often some codecs used. There are in different languages that we use. So there are different ways how these samples can differ from what we trained our models on. One of the most known examples of such generalization issue was highlighted in Does Audio Deepfake Generalize paper by Miller et al. And in 2022, the authors created the data set in the wild. So they gathered around 40 hours of speech from the internet that were different utterances by lots of VIPs, along with that were bona fide samples, along with the deepfakes that were also found on the internet. So the authors evaluated commonly used architectures, and they first evaluated them on ASV 2019 dataset. The best results that they obtained there was around 1.5% EER, which is a very good result. The very same models, however, tested in the wild provided much worse performance. The best performance there was around 33% EER, and many of the models were even worse than random guessing. So the EERs were greater than 50%. Currently, in the wild is currently used in many papers. It's a benchmarking data set, and new methods, the methods that are currently introduced, they often score single-digit performances, single-digit ERs on this data set. However, the principle remains. So if we have a different data, then often we can have this generalization issue. It's difficult. It's difficult to detect deepfakes, even though we just have to say if it's fake or not. We have a binary classification problem. There's not a single indicator that something is fake. It's difficult to pinpoint a single characteristic of audio file. There are lots of places where these artifacts may appear, and they're located both in spectral and temporal dimension. And oftentimes, it simply depends on the generator that we're currently using. So throughout the years, there were many papers that focused on assessing where these discriminative features lie and what the information we gain from this. The authors were looking for some particular parts of the audio files, and if this given part gives us the best performance. So if we can achieve the best performance using this particular part, this means that this is the best distinguishing characteristic, and therefore we can say that this is where these discriminative features lie. Detection is based on high frequencies. Detection is based on some particular frequency bands. Slightly different problem, replay attacks, but here these discriminative features lie in the upper part of 6 to 8 frequency part or silence parts and high energy speech. Depending on the data set, depending on the models, this information can be located, in fact, everywhere. So how do we combat the generalization? Simple, however, not an easy way to do it is larger and more diverse data sets. So if we expose our models to more different generation techniques, first of all, we will typically we improve on the very attacks. So if we have the attacks in our training data set, then we will probably be good at them. And it often helps with other unseen methods. If we have 5-gen diffusion-based generators, then, well, there's a better chance that we will perform on yet another diffusion-based generator than if we wouldn't have any such methods in our training data set. Neural network-based frontends. So a few years ago, what we typically did is we, based on these digital signal processing-based representations, we were using either raw audio, and that was the input to the models, or we were basing on these spectrograms, MFCCs, things like that, algorithmic approaches. However, models that are trained on humongous data sets, trained in self-supervised learning fashion or weakly supervised ways, models like Wave2Vec, Hubert, or Whisper, they return very good embeddings. They return very nice representations that allow us, when we fine-tune it, even if we don't fine-tune it and we use them out of the box, but even when we fine-tune it to this downstream task that is deepfake detection, we get very nice generalization performance. These models, these features are simply better. The third thing is training procedures. So at its core, deepfake detection is binary classification task. However, we can extend it. We can extend it either by some manipulations of data sets, so the techniques of data sets joining like attack agnostic data set, or by different training paradigms, like for instance, one-class learning. Also, data augmentation. The samples out there are different from what we have in our training data set. Let's do something about it so they are, well, less different. And for that, we use techniques like Robust, libraries like augmentations, or we add, for instance, background music. And typically, what we use is, for instance, Musan dataset. So attack agnostic dataset. In this paper was written back in 2022. Back then, we already all experienced that this fast pace of the Gen AI development leads to increasing number of speech synthesis solutions. From our perspective, we have more and more attacks that one could use to attack a system. This also meant that because of this fast pace, our data sets are constantly outdated. And because we have outdated data set, if we're training on the data sets that, for instance, don't have some new approaches. It's not even about the iterative work of just slight modification to the existing synthesizers, but also like the novel approaches. If we don't have new methods, then typically what we would have is we would underperform on them because our models haven't seen any of such artifacts. Back then, there weren't also that many data sets out there. And because there aren't many data sets and we have the problem of many new methods, we would like to somehow assess our performance. And by performance, I'm mainly talking about generalization and stabilization. We'd like to assess it based on what we currently have. So we would like to use the info that we already have to select a most future-proof model. So attack agnostic dataset, assessing generalization and stability of these detectors, and we use it, we base on available data sets. We would analyze how different combinations of the attacks in training subset influence test results. You can think of cross-validation. In cross-validation, we distribute samples across these different faults, splits. We distribute them randomly, but naturally with respect to classes and things like that. In attack agnostic dataset, these samples are also distributed across these different splits. However, here we have these different criteria. So by criteria, I mean we would like to expose our detectors to different scenarios. What if scenarios? Why attack agnostic? It's a framework. It can be easily extended with other data sets, generation methods. You can increase number of faults, increase number of methods in each particular fault, create your own scenarios. So here's a little sneak peek of what this AAD, what is it about? So here's a breakdown of wavefake dataset, one of the datasets that we used in the original paper. And here what we see are different rectangles of different colors. Let's focus on the yellow one. So full band Melgan, yellow, and multi-band Melgan, also yellow. Same colors denote similar methods. And we would like to move things around so we can expose our model to different scenarios. We, in the paper, introduced information limitation and information joining scenarios. Let's focus on these Melgans. Fault number 2, information limitation. We would like to limit the info that we have an access to during training. Therefore, only multi-band Melgan is used in training, and we would like to see how do we perform on full-band Melgan when it's in test subset. Whereas information joining, let's take both these methods in training dataset and see how does it affect the performance. So we have different results on different sub-data sets, and how do we interpret that? So if the results between these faults differ significantly, this means that these particular arrangements, these particular subsets of the data sets influence models significantly. So this means that it's not very stable, and if the results are bad on the test set, they do not generalize well, these methods. And that's just high-level overview. When we dive into the topic and if we look at the particular methods, run additional trainings, etc., then we have this deeper analysis, and we can, for instance, see which attacks contribute most significantly, and this is both in terms of positively and negatively to the results. So what we did, like to summarize, framework where we have this joint division of these attacks among subsets, and this allows us to assess generalization and stabilization. We would like to select the most future-proof model based on what data sets we currently have. It's framework-like, so it can be easily extendable to databases, other splits, additional scenarios, so on and so forth. It's 3 years old, almost 4 years old. Is it still relevant in 2025? I think so. We no longer have a problem of having just few available data sets, so we can leverage attack agnostic data sets in a slightly different way. we can create splits by either working on the dataset level. So let's have split based on these datasets and test them on other datasets, or maybe some specific methods from different datasets. There are datasets that are, for instance, oriented on diffusion-based methods. Let's see how this corresponds to the performance on these totally in the wild samples. There are many ways how to use it. Oh, and I attached a link to the implementation down below. MLAT, the second paper, also concerning datasets, multi-language audio anti-spoofing dataset. So this is the largest multi-language deepfake detection dataset. We constantly, continuously update it. Right now it's at version 6, and it's Apache 2 license. The dataset is available at Fraunhofer OnCloud and on Hugging Face. So what was the motivation for creating MLAT? We noticed that there's a limited language diversity, or there was a limited language diversity of the training data sets. So deepfakes are attacking people all over the world. You have deepfakes that are in all different languages. However, the training datasets primarily focus on a couple of languages with English and Chinese as the most commonly existing ones. The other thing is that these anti-spoofing or deepfake detection dataset quickly become outdated, as I mentioned with attack agnostic dataset. These new models are introduced every day, so it's crucial to have methods that are datasets that can be constantly updated, to just have resources, just to have data to either evaluate our models or even to train our models on these new generators. Couple information, a few things about MLAT. So we generate the spoofed samples for MLAT using couple of sources. Primarily, these are GitHub repositories. So paper implementations, they often come with the pre-trained models, and we use them. There are lots of models on Hugging Face, and also toolkits like, for instance, Koki AI, which we used very much in first versions of MLAT. MLAT is based on MAI Lab's speech dataset. So this is bona fide speech in English, French, German, Italian, Polish, Russian, Spanish, and Ukrainian. And we use these utterances to generate spoofed utterances. So in other words, MLAT is composed only of spoofed utterances. This is the only part that we're distributing. If someone would like to train a model and would need bona fide data, then MAI Labs is a go-to dataset here. How do we do it? So for each language given model supports, we select 1,000 random transcripts. MAI Labs contains 8 languages, and if we would like to generate samples outside of these languages, then we simply translate transcript from MAI Labs English subset. Then we create naturally these spoofed utterances, and whenever it's possible, so whenever model is multi-speaker or is voice cloning solution, then we use speaker references to have as diverse data set in terms of the speakers. The outputs are later saved as 22 kilohertz, 16-bit wave files with a little bit of metadata like path, reference to the original file that we're spoofing, language, is it original language, so is it from MAI Labs, the duration, training data. It's not always disclosed by the authors of these generators, but whenever it's possible, we try to write down what was the data used to train this synthesis model name, architecture, and corresponding transcript. V6. So in these 15 months, we increased the duration over 2.5 times. We added 15 new languages, around 40 models, and 20 new architectures. So right now, V6 was released in April 25. So what is it? 1 month ago. We currently have over 420 hours of speech, 38 languages, 91 TTS models. and these are these newest models out there. So DiaTTS, MegaTTS, Fish, Zonos, Spark, Sesame, or Orpheus. And starting with version 6 of MLAT, we also are adding commercial systems. So we also, so in V6, we added Resemble AI. On the right, you see the table with the durations for each of the generator. And well, for instance, VITs. There are many implementations of VITs in all different languages. Therefore, we have a little bit of samples here. XTTS natively supports what is it six languages or even more. So there are also lots of utterances here. However, for some generators, these generators are single speaker, single language, so there's not much that we can do. However, there are 91 as of now. Regarding languages, so we have coverage in, I guess, all major language groups. The problem, that's the way it is in synthesis world, that these pre-trained models are often trained on languages like English, German, Chinese, and therefore when we would like to use them to synthesize speech, we can synthesize only these languages. Therefore there are lots of English samples here, but we also have these samples that have less pre-trained models, and we're eagerly trying to expand to other languages and also increase number of samples in each of these already existing languages. So to summarize, MLAT, multi-language deepfake dataset, we constantly update it with recent TTS methods, and it can be used either as a training dataset or as a test dataset. As a test dataset, then that's a dataset where every now and then you can check if there's a new version and see if your model is performing well against these new generation techniques. Or training, then you would need to use bona fide data. You need to add it. Either you have it or use the go-to dataset that we reference in the paper, that is MAI Labs. It can also be used in source tracing. Source tracing is a topic of attributing fake samples. So we're interested in not saying whether it's fake or not. We assume that we know it already. We know it's a fake sample, and we would like to trace what technology, what generator, what was used in fact to generate such an utterance. And therefore, I would also like to invite you to source tracing the origins of synthetic or manipulated speech. That's a special session that I had a pleasure to co-organize, and it will be at Interspeech this year, 2025. So generalization, but there's also robustness. The second problem is when we degrade our audio samples, then we often notice that this negatively influences the effectiveness of our systems. And there are two ways how there are two types of these degradations. First of all, they can be non-intentional. So this is data compression. Deepfakes are spread across internet. Every time we upload, every time we download them from the internet, every time someone shares it, etc., there's compression involved. Many times, different platforms, lots of shares. These samples there are many layers of compression on top of the original sample. And this is non-intentional, that's the way it is. However, there are also intentional degradation types, and they are adversarial examples. So they are these specially crafted samples that aim to attack AI systems. They are these imperceptible changes that totally change the prediction of our system. Typically, we distinguish two approaches, two paradigms, so to say. This is white box attacks, and in this particular scenario, an adversary has an access to the whole system. So the attacks are prepared based on intel gathered from the very system that we're currently attacking. The second approach is black box attacks, and there we have limited knowledge. We either do it by querying the system, so we just have some bits of information that we use to prepare such modified sample, or we even use some additional systems. So we use other models, other system to craft such an example. defense against adversarial attacks on audio deepfake detection. So this is the paper when we focused on adversarial attacks. One could say that adversarial examples decreasing effectiveness of AI models is, so to say, general knowledge in machine learning or artificial intelligence. And there were papers that covered adversarial attacks on anti-spoofing. They were there before. However, there weren't papers on deepfake detection. And well, we both, like in both fields, we use generators. We're trying to detect if something was spoofed or not, if something was generated or not. However, there are two crucial differences that made us work on this topic. The first one is target. In ASV, in anti-spoofing, we're targeting ASV system. So we're trying to trick computer. Computer wouldn't care that much about the distortions or the naturalness of these samples, at least not as much as a human. So the target of deepfake attacks. That's the first thing, target. The second thing is the media, the environment in which the samples are distributed or spread. In deepfakes, these samples are spread across the internet. As I said, lots of compression involved. This is also reflected in ASV 21 datasets, where we see that we have LA and DF subsets, where DF subset is well, it contains all sorts of codecs. So because the differences between these two tasks, we wanted to examine influence on deepfake classifiers and hopefully propose some defense measures. The task or the problem is also crucial because, well, there were only few data sets that the defender could use to train a model. And there were only few go-to architectures that one could use. And because of this limited resources, limited number of methods, limited number of data sets, an attacker could have a good guess of what was involved in creation of this deepfake system, and therefore this gives a leverage to this person. Therefore, also in paper, we do not reference the attacks as black box and instead use transferability name. We used three attacks. We used
Sorry,
sorry.
Piotr. Here is one question in the
Oh,
chat.
okay.
Can you see it? Since most neural network-based systems map the patterns of the data fed to it, is it ever possible to design a system which can identity spoofing attack generated in a complete different way? Thank you.
One second.
I think it's more about source tracing.
Better to design a system which can identify generated in a completely. Okay, so we're talking about out of distribution problem, I think here. So is it possible? There's so in source tracing there's this way to say that data is out of distribution. I think it would be difficult to say that some utterance where we never saw samples of this vendor or this generation method to say that it's this particular method. Therefore, we use this out of domain flag or this whole approach to do open set recognition, if I recall the name, or have this out of distribution checking. Yes. Okay, I'll continue. Where was I? Yes. Okay. Attack levels. So what we did is we used three attacks: FGSM, PGDL2, and FAB, and for each of them we selected three power levels of these attacks. These power levels corresponded to both effectiveness. Typically, the greater the value, the stronger the attack, the more devastating the attack, and also they were the distortions were more audible. So I'll present you two examples. The first will be original sample.
More than this, Griffiths took the police to a field where
Was it audible? Okay, great. So this is the bona fide sample or on unaltered data. And here is, let's first start maybe with FAB. So the distortion that we were able to have using adversarial attacks. And this distortion successfully flipped the prediction. So it was predicted as bona fide or spoof, and the system, after applying this modification, predicted something else.
More than this, Griffiths took the police to a field where
So this is a good case where the distortions are not that audible. However,
more than this, Griffiths took the police to a field where
however, sometimes these distortions can be audible, but even if, then we can always, as an attacker, say that it's malfunction of the equipment, environmental noise, and so on and so on. So this means that this is, well, difficult because they are not very audible, these differences. And as we will see in a second, they are devastating to the results. So the baseline is can be seen on the right-hand side here. For models like LCNN, SpecRNet, and RONet3, the average ER that we obtained on the data sets was around 2%. When we attacked the very systems using white box attacks, we were able to significantly degrade the results. The biggest impact was on SpecRNet with PGDL2, and we were able to get 99% ER. So almost all predictions were false. In transferability attacks, what we did is we trained 3 models. So we used the models that we originally trained and attacked them using the other 2. So LCNN was attacked using SpecRNet and RONet, with using FGSM, using PGDL2, and so on and so forth. So here the results were less devastating, so they were less impactful. However, still for some cases we were able to, first of all, they contribute to the decrease in the results, but the worst, so the most impactful decrease was, can be seen here, 48% EER. Okay, so we know there's a problem with adversarial attacks. How do we defend ourselves against it? The first thing would be by either, for instance, preprocessing inputs. There are some additional information and additional perturbations that are added to audio file. Let's delete it by using different kinds of denoising. Adversarial training is what is typically used, and there are different approaches. There's a whole lot of research on this topic. Train on original data set and then fine-tune it on adversarial data. This is the original approach to the problem. Instead of using only adversarial data, use mix of adversarial and original data, or maybe some adaptive techniques. So techniques where we don't apply the same strategy and focus differently depending on the attack that the sample in training dataset was modified with. So what we did in our paper, we tried these baseline approaches of fine-tuning using adversarial data or using a mix of them. However, we always ended up in a poor performance. So the detectors that we trained, they always focused on a subset of the attacks, totally disregarding others. So we could have been good at, for let's say, PGDL2. However, on FAB and FGSM, there was almost no improvement. So we came up with our way to do adaptive adversarial training. The algorithm is outlined on the right. In the paper, we have an ablation study with all these parameters and all these approaches described. The most important in this approach is the intuition that we would like to focus on the difficult attack. So what we did is we selected samples for the next training batch based on their difficulty, because before that the model was focusing on the easy attacks. And right now we would like to focus on currently most difficult attack. And how do we do it? For that, we used sampling vector. So what does it mean that the attack is difficult? It means that the loss function for this particular class of attacks, let's say PGD, is large. The value is large, the attack is difficult, and therefore with greater probability we would like to pick it in the next batch. As I said, there are a few control mechanisms based on the experiments that we run. So things like we would like to threshold loss function. There's a running mean used here, or also attack to non-attack ratio, because while we would like to improve on adversarial data, we would also like to still perform well on this unaltered, on this original approach. So in terms of white box attacks, it helped. It helped significantly, because the worst ER of 99% was decreased down to 9%. So this is still an attack. An adversary has still an access to the model and can still attack it, but we no longer have ERs of 50% or more. On transferability attacks, the results were less conclusive, because we only had improvement in about half of the cases. So from 48%, we decreased it down to 10%. Unfortunately, what we saw is that we had decreased the decreased performance on original data, and from 2% on the original unaltered data, the performance of our model was around 8.8%. So adversarial attacks, they are difficult to create, because you need some sorts of models, either the model that you're attacking or other deepfake detection models. They are difficult to create, but they are threat to these systems. We introduced adaptive adversarial attack and adversarial training, and it improved performance. However, it worsened results on unaltered data. Still, I think it's worth to include some sort of these adversarial training and adversarial attacks countermeasures to prepare systems against such attacks. However, we should decide whether is it more like a danger to us, or would we rather stick to the original problem of unaltered spoofing. The last paper that I wanted to talk about is DEEPEN, so penetration testing for audio deepfake detection.
Sorry, Piotr. We have
yes.
another question, maybe for your previous section, that about your recent interspeech paper. Do you see?
Maybe is it okay to me to answer after I
Of
do a
course,
presentation,
sure.
or okay?
Yes. Yeah, sorry.
I'll get to it. Nice question, thank you. So regarding DEEPEN is a so what we saw is that these alterations of the audio samples can be done by either adversarial attacks or standard digital signal processing operations, and we would like to focus on the latter one. So it's crucial to highlight these vulnerabilities in popular detection methods and somehow address them. DEEPEN is an open source toolkit that allows you to evaluate robustness of these deepfake classifiers. And for that, we use different types of digital signal processing modifications, all sorts of them, from adding some information like music or noise, through simulating echo, manipulating frequencies, adding noises, or shifting pitch. This is, once again, an agnostic method, a framework, and no matter if it's audio, then you can run DEEPEN on it. However, in our paper, we focused on ASV spoof and MLAT. What can you use DEEPEN for? You can use DEEPEN for evaluating performance and finding these weak spots, these weak points of your solution, and hopefully do something about it. So the DEEPEN was created in the original paper. We used 200 bona fide and spoof samples, and we modified them using all these attacks that we introduced. So this resulted in 2 subsets of 7,200 samples, and they were partitioned into train and test subsets that were used in later experiments. Okay, so we first started with open source models, implementations on GitHub that had existing checkpoints that we could use. And we used models like RawPC darts, LCNN, ROGAT, RONET2, Whisper, and Wave2Vec Assist. We evaluated the models on 2 data sets, so you can see like these column parts here on ASV and on MLAT, with respect to the label of the sample, so bona fide up there and down here spoof, And we reported performance according to each of the attacks that we ran. So background music, background noise, and so on. There are a few observations that we had. So first of all, MLAT was more challenging than ASV spoof, but it makes sense because majority of these models were trained on ASV spoof 2019, and MLAT contains these newer methods. Generalization issue. That's the example of this generalization issue. The models, well, there were also different performances of these models. So Wave2Vec is the best out there. It's significantly better than models like DARS or WhisperDF. And the same thing can be said about the attacks. There are better attacks and these less effective. So attacks like add background music and add background noise here were the most effective ones. Oh, and also time stretch. It's important also to highlight that some of the attacks were better at turning spoof into bona fide and the others at making bona fide appear as spoof. So for instance, what is it? Add background music? Yes, add background music here allows us to effectively hide bona fide as spoofs. However, the other way around, it does not work that well. Conversely, silence injection or high pass filter allows us to effectively hide spoofs as bona fides. We also evaluated commercial systems, and we evaluated 3 of them. We do not disclose names due to different agreements. Number 1 and number 2 here, they are vulnerable to few attacks. The first one was more exposed. It primarily detected samples as bona fide, as spoof. So it was biased towards spoofs. System 1 and System 2. So we also have some observations about the attacks. The most devastating were pitch shift and time stretch, which effectively hit bona fides as spoofs. Therefore, if you would like to go this way, then use these attacks. However, the other way around, high pass filter seen here or add background music, they are better at hiding these types of samples. So even though we see this table is more green than the previous one, the performances are better than in case of open source models. However, still, no matter how good these models were, there were still few attacks that were able to compromise these systems. So what can we do about it? We know that our model underperforms on particular sets of attacks. How can we leverage this knowledge? So we used, for the experiments, we used Wave2Vec as the best model from these open source models. And we trained it and exposed it to 4 scenarios. The first one, no adaptive defense. So we just trained the model. Using adaptive defense, but only using one attack, using all attacks, and using subset of the attacks. What do I mean by using the attacks? By using the attacks, we simply do data augmentation using the very techniques that were previously used to attack us. We now leverage that as data augmentation technique. Why do we need subset of the attacks? So for naively, we could just use all the existing methods, all the existing attacks, but this would first of all increase the requirements, the time that we need to train a system. It wouldn't necessarily give us much of the insights of how model really works. Maybe we can use only a subset of the attacks, have a good insight, have a good interpretability of what's happening there, and hopefully get same or similar performance. So yet another algorithm, but the intuition here is that for the defense, for this data augmentation technique to be included in the set that we would like to use it has to fulfill 2 criteria. The first one was that it should defend better than against some attack, we should defend better than anything else. So we're the best against, let's say, echo. At the same time, even though we're best against other data augmentation techniques, we should still obviously be better than this no defense scenario. And we had a threshold of 5%. So if the countermeasure method is the best of all and better than the baseline, we take it toward the subset. And we ended up with such a subset that was used for the performances that can be seen here. So columns here denote the attack that was performed on the samples. Adaptive defense here is, these are the very same attacks that were used by us as these data augmentation techniques. Each cell shows the relative performance. So let's look at echo. If we use adaptive defense of echo, so if we augment our data using echo and we compare it against the samples that were attacked using echo, we are 32.6% better than the baseline, so of not doing anything, no defense at all. The cells that are highlighted here in blue, they fulfill the first criteria, so they are the improvement is larger than 5%. We're 5% or more better than the baseline. So when we retrain using all, so naive approach, take all the attacks, retrain model, no defense, we improve over no defense by 13%, and the decrease on unaltered data is only 0.3%. However, when we use only a subset of these attacks picked based on the algorithm, we only use 9 out of 17 attacks. It looks that, well, some of these attacks substitute for the other attacks, and the performance that we get is similar. It's 0.3% less in the overall performance on altered data, whereas on the unaltered data, the performance drop is the same. So adversarial attacks were difficult to create. The attacks that we use here are easy to prepare. It can be done either by some toolkits or by some audio manipulation programs, and they significantly decrease the performance of both open source and existing commercial products. From the perspective of an adversary, we should carefully select the attack to maximize the damage. So if we want to make spoof appear as bona fide, pick something. If we want to make it another way around, it might be something else that would maximize the damage here. In terms of adversarial defense, we can defend ourselves against these attacks. And the cost is not much because that's just a slight degradation on unaltered data. And that's only using just a subset of the attacks. So we can indeed have a pretty good view on what the model is learning, what attacks can give us the best performance. So to summarize these 4 papers, in these papers, we showed that the performance of both these open source but also these commercial deepfake detection systems, they do suffer from 2 things, namely generalization and resilience or robustness against these different attacks. And the threat is real. Threat is real because, first of all, the development of Gen AI. Methods are better. Methods are more accessible, methods are cheaper. These TTS or VC technologies, everyone can create a deepfake, and this means that there will be more and more of these samples out there. Also, adversarial attacks, not only adversarial attacks that are difficult to create, but also these simple modifications can decrease the performance. So we should somehow react. And how can we do it? Well, we should take it into account when we are developing our detection systems. We showed that based on these methods that we introduced, we can improve both generalization from the datasets perspective, so using AAD or MLAT, or from the training protocols, training paradigms perspective that primarily aims for the better robustness, so by using adaptive training or adaptive defense. I wrote down 2 bullet points about the future work. So what we would like to have ideally. So when it comes to resilience against the attack, ideally, we would like to, don't have performance drop on unaltered data. In adversarial attacks, there was a performance drop. In adaptive defense, there was still a drop, but it wasn't that significant. Hopefully, we would have a free in the sense of not having any decrease, free methods how to defend ourselves against these attacks. And the second thing, generalization improvements. So ideally, we wouldn't like to constantly update our models based on these new data sets. I think that based on what self-supervised learning models gave us a few years ago, this boost in generalization capabilities of the models, there's still some ways to address it, and yeah, I have a positive feelings about this generalization capabilities. I'll very quickly share with you two free or open source things that we did at Resemble in last month. The first is Resemble AI WhatsApp bot. So that's a free deepfake detection WhatsApp bot. You need to text this number here on WhatsApp, and you can send either audio, image, or video. And what we do is we run free deepfake detection on these samples, along with some misinformation or disinformation evaluation for the particular samples. And the other thing is Chatterbox. This is a new text-to-speech model. It allows you to do zero-shot voice cloning. It's MIT licensed, so it's open code along with model weights. We do care about security and safety. Therefore, all of these samples that you generate using Chatterbox are watermarked. And for watermarking, we use our PERT neural watermarker. So feel free to check it out. The links are attached. Yes, these are the references that I used. And I would like to thank you very much for the attention. And if you have some questions, I'd be glad to answer them.